So far in this chapter, we have learned about nomenclature and physical properties of aldehydes and ketones. Now we're going to be looking at how to synthesize aldehydes and ketones. Many of the techniques that we have covered in previous chapters can be applied in synthesizing ketones and aldehydes. As you can see in this example, what we are using is Grignard reagent. And we use this technique in chapter 10, how to synthesize secondary alcohol. Basically, what you need is a Grignard reagent, which is nucleophilic, to attack your aldehyde with the carbonyl group, which is electrophilic carbon right there. Then by further acidification of your solution, you're going to get a secondary alcohol. And as you know, secondary alcohol can easily be oxidized to a ketone. You could use Grignard reagent, and then, for aldehyde, you could use formaldehyde, do acidification, and then you're going to get primary alcohol. And primary alcohol with a mild oxidizing agent like PCC to change it to an aldehyde. Okay, this is something that we saw in the chapter that we were covering, alkenes. And this is an example of oxidative cleavage of an alkene with the ozone. And in this type of reaction, as you can tell, the double bond in here breaks down and it's going to give you these products. The products could be two ketones, two aldehydes and ketones, depending what kind of groups we have on the carbons in here. If we have one R group, one hydrogen, we will get an aldehyde. If we have two R groups, we get a ketone, okay? And if you have hydrogen here, and hydrogen there, and hydrogen there, hydrogen here, you just get formaldehyde. This is how to use Friedel-Crafts acylation to synthesize ketones. As you can tell, you need the Lewis acid, right? And you need acid chloride, and you need an aromatic compound. And when the reaction is done, you're going to end up with a ketone. And this type of ketones, one of the group that you have on the carbonyl carbon is always aromatic. Like in this example, they both are aromatic. But in this one is aromatic, one is not aromatic. This is synthesizing ketones using alkynes. If we use the mercury 2 sulfate sulfuric acid then add water, what is going to happen? The alkyne is going to change to enol. When the enol is formed, since it's not stable, then you're going to get tautomerization. Tautomerization means this hydrogen is going to move to this carbon, and this pi bond is going to move between carbon and oxygen, and it's going to shift to ketone. And then, as you can tell, in order for this tautomerization happen, then the compound change to the ketone, we need to add acid to the mixture to move the equilibrium toward the ketone, because these two, they exist in the equilibrium. And this is called synthesizing ketone from alkynes with the Markovnikov orientation. Here are a couple more examples of changing alkynes to ketones. But if you look at your textbook, page 891, you will see that alkynes can be used to synthesize aldehydes also, but not with these reagents. It means you have to do hydroboration oxidation. To do hydroboration oxidation of alkynes, as we have covered before, you need diethylamine borohydride, hydrogen peroxide in sodium hydroxide. Since the whole oxidation is happening in a basic medium, if you get enol, enol goes through tautomerization, but the product would not be a ketone, it would be an aldehyde, because in here you will have sodium hydroxide. You will not have protons as is shown in here. And so that's how to change alkynes to aldehyde. Synthesis of ketones from carboxylic acid is something that we have not covered yet. So if you look at your textbook on page 893, you see this type of synthesis in more detail. The first step of synthesizing ketone from carboxylic acid is to remove this acidic proton. To remove the acidic proton, you have two choices. You could use lithium hydroxide, or you can actually use your organolithium product that you want to add right there. So the first purpose is to remove that hydrogen, to put the lithium there, right? And when that carboxylate ion is formed, then the other organolithium product would attack that carbon, and you get a anion like it is shown in here. But when you acidify the solution, the dianion is going to change to a hydrate. But the hydrate that is forming here is not very stable, and it loses water quickly to produce ketone. Okay, in here we are learning how to make ketones and aldehydes from nitriles. What is shown in here, how to use nitrile to make a ketone. And this technique only works for synthesizing ketone. So if you want to change a nitrile to a ketone, you need to add Grignard reagent to your solution. When you add Grignard reagent to the solution, Grignard reagent will attack the electrophilic carbon. And when the attack is made, you get what is known as magnesium salt of imine. Imines are compounds like shown in here, and imines are organic compounds when carbon and nitrogen are doubly bonded. And when the salt of imines are formed, then you can add acid to change the salt to imine. But if you want to change the imine to ketone, then you need to acid hydrolyze the imine. That's something that we learn in the next chapter also, when we are learning about the amines and the reactions of amines. So that's how amines are changed to ketones by acid hydrolyzed, okay? And here, amines, if they are formed, they are stable, they can be removed from the mixture as amine. We don't have to go all the way there if we don't need to. Here is an example how to change nitrile to aldehyde. If you are going to change nitrile to aldehyde, you need to use a modified reducing agent. If you use aluminum hydride is a strong reducing agent. When the aldehyde is formed, it can be further reduced to an alcohol. That's why here aluminum hydride is modified and is changed to diisobutyl aluminum hydride. So to change a nitrile to an aldehyde, we need to use a mild reducing agent like the one that is shown in here and further acidify it. In the next two slides, we will learn how to synthesize aldehydes and ketones from acid chloride and also ester. But first, we need to learn how to synthesize acid chloride. As we have seen before, one of the ways that you could make acid chloride is to react carboxylic acid with thionyl chloride to get acid chloride. And the reason that you want to change the acid to acid chloride because acid chloride is much better reagent, much more reactive than the acid. And as you know, the Cl is a much better leaving group than OH. In the previous slide, we learned how to synthesize acid chloride. Now, we're going to be looking at how to change acid chloride to aldehyde. Again, you can reduce the acid chloride to aldehyde, but in order to do it, you need to use mild reducing agent. Because if you use lithium aluminum hydride, again, lithium aluminum hydride, as it was mentioned in previous slides, is a strong reducing agent, and it will change the aldehyde completely to alcohol. So in order to prevent aldehyde to change to alcohol, you need to modify that reducing agent that we typically use, like lithium aluminum hydride, and here is the modified version of the reducing agent that is used in your textbook. If you look at page 896, they show you how to use acid chloride and organolithium or Grignard reagent to change acid chloride to ketone. If you use a Grignard reagent and treat it with the acid chloride, you're going to get ketone, but then the ketone is going to change to an oxide ion, then you eventually can change to a tertiary alcohol. So in order to prevent that, you're going to be treating your acid chloride with Gilman reagent. Gilman reagent, as is shown in here, is dialkyl cuprate reagent, and basically it will provide one nucleophilic R group that will attack this carbon, and you will get your ketone. And when the ketone is formed, is stable, and it won't go any further oxidation to alcohol or something like that.